Welcome everyone, appreciate your time and wherever you might be, good morning, good afternoon, and good evening. Today, we're going to talk a little bit about sampling in relation to patient safety and risk. It's a very dense topic, so we're going to try and keep it snappy for you and get through some items that are difficult to understand. So I want to start off with one of my favorite quotes because I'm sure for all the industrial experimentalists in the audience out there, you really appreciate what this says and how it's our constant battle to try and make sense out of the chaos that we're often confronted with. So let's take a look at an example for just a second. And I gotta ask everybody, does this look like a mistake to you? Let's take a look. How's it? Are we able to do that? Okay, it looks like we're getting choppy video. There we go. This is really my favorite part right here. Ooh. So hopefully your experimental programs don't all end like this. And the question is, does that look like a mistake to you? Well, let's consider how it was framed up in terms of a key point that I want to focus on in the presentation, which is Deming's point number 8 about driving out fear. A lot of people in the industrial experimentation community tend to think that this is really part of the human relations part of building a business. And sure, it has something to do with that. I'm going to frame it up more in terms of mistakes and false positives and false negatives. Which are you more fearful of making? And which do you take more seriously as you develop a test program? Well, we all know, and for those that aren't that familiar, that there are two types of errors that can be made. We'll classify them in this case as producer's risk, a type 1, or consumer's risk, a type 2 error. Looking back at that video we just saw, Musk actually called it a successful ascent. They got all the data they needed, even though it ended in a fire disaster. So regardless of what you might be more fearful of making in your experimental career, a producer's risk error or a consumer's risk error, the punchline, no one in the organization is going to care because as soon as that mistake is made, you're over budget and behind schedule. So let's look at how we can combat some of these things. That SpaceX mistake, that was really just an expensive sample. And we actually know exactly how much it cost. This is important, and we're going to talk more about it as we get through the talk here quickly. But it really identifies the crux of what the battle for perfect information is, right? It's this continual push and pull between fast, cheap, and great, as I like to call it. And the idea that we have in our experimental programs, through the selection of samples, the ability to get closer to great without giving up either of the other two. And we're going to look at that in some detail. We're going to talk through the stepwise analysis of how input changes to your sample selection, specifically in relation to an operational characteristic curve, can affect your patient risk. So let's take a look. All right, so how's it all calculated? I'm not going to put you to sleep with math today. We're going to deal with graphs because that's always a little bit easier to comprehend. And in a short 20-minute talk about this topic, it's faster for everyone to grasp. But I always get asked this question, whenever someone comes to me trying to think about how to develop an experimental program, everyone grasps onto the concept of, well, how big should my sample size be? Well, 30. Everybody uses 30, right? It's a very popular number. And I often get asked, why is it 30? Well, let's take a look at that. There is this curve called the power curve, and we look for the optimal use of resources in an experimentation program. Why? Very often our experimental programs are destructive or at least contaminatory, meaning you test a sample, you can't reuse it for anything else because you contaminated it with the effects of the test that you're performing. We use very often, and it's quite popular, I get asked this all the time too, a binomial distribution with a C=0 acceptance as a test algorithm. Well, it's interesting when you look at these two because there's a convergence. As the sample size goes up, the two graphs for those distributions, the geometric distribution shapes, they converge, they come together. And where that happens is actually right at, next click please, where the sample size is approximately 30. So if you ever wondered, where does 30 come from? This is where it comes from. It comes from the fact that your estimations, the binomial distribution and the normal distribution, usually based on a much larger population, they converge right at about n=30. And that gives you an optimal use of resources. Now, that said, is that the number you should use in your samples all the time, every time? No, it's not. We're going to look at and try to understand why that is so. And let's move forward and take a look. What you're trying to estimate here is the risk and the potential costs built into your experimental program. What are the pressures you have? Well, they're the little red devil on the right. Sometimes it's built in, hubris, right? Having an aggressive confidence that your test is going to work out just perfectly fine. Maybe you've got some, cost pressure from your CFO. You got to keep your experimental costs down because it's an expensive device, and I'll bet it is. And there's always pressure to go fast. That's pretty common in any company to try and get a product to market quickly. So you have those pressures driving you. What I want to encourage the audience to think about is what's really on the right. Understand differential costs of experimentation, right? Think about how much it tests to cost each additional unit. We're going to look at that in just a second and why that's important. Make sure you think about the costs of each kind of error you can make, a producer's mistake or a consumer, or in this case, a patient error, right? Think about progressive experimentation. And we're going to talk through that a little bit using double sampling plans here in just a minute. And I encourage everyone out there listening to think about what I call high veto power testing. Don't necessarily start your testing program with those items that are easy to test, right? Sometimes that's fruitful, but in more cases, it's actually more important to test those things in your device that are high veto power and could smash the whole program. That's where you start. It's a high veto power experimentation because it brings the whole program to a screeching halt. Don't be afraid of it. That's that drive out fear thing. Start there. All right, let's move on, because that brings us back to this battle for perfect information. All right, let's say you've gone ahead and picked an experimental algorithm. For sake of argument, we'll say it's a binomial distribution. We're going to sample without replacement. We'll set up a C=0 type of acceptance, and you had a failure. What now? Now is when you really want perfect information, isn't it? Well, let's go back to thinking about the reason I mentioned understanding your costs. What's an additional sample going to cost you? Is it cheap or is it really expensive? Just as important, what's your delay time? How hard is it to repeat your experimentation? Is it inexpensive to do, or is it really expensive multi-site type of trial stuff, right? Those are important elements to think through because they're all going to play into understanding now that you've had a failure in your experimentation. You need to understand the operational characteristic curve of your universe of parts or assemblies or devices that you're going to take and test, and maybe augment the sample size with more. All of that's necessary to understand to balance your risk with data so that you can improve your patient safety. All right, remember, you've already had a failure, okay? So let's look at this OC curve thing, right? I don't want to try and demystify it for everybody very quickly. This curve shows you where your confidence and power are located in the curve. So we'll start looking there. Let's just see where things shake out. You've got a producer's risk and you've got a consumer's risk. Let's take a look. Okay, your consumer's risk is shown down here at the bottom. That's your patient. right? That's how we consider the quality of an overall lot. Okay, if we've got bad quality, that means our patients are going to see that. That's not great, right? At the top is where we have our producers or manufacturers risk. That's characterized by confidence. All of that relates to the quality of the lot or the lot's total percent defective, okay? The way we're going to look at that and the way I want you to start thinking about it is what's the probability point at which you would accept this really poor quality? That's the important key point to think about your patient's risk. So as we set up our programs, right, we're going to want to think through incremental experimentation, increasing that consumer's risk down there at the bottom. That's higher patient risk. And that's why you want to be very cognizant of it as you go through these experimental test programs. Okay, let's move forward. So we're going to talk about a double sampling approach because you've essentially boxed yourself into that situation. If you started out with that binomial, a C equals 0, and you had a failure, you're going to be asked to augment your sample most likely and figure out if you have sufficient quality in that lot to actually be able to release product. Probably a very common occurrence for many of you out there in the field, okay? So since you're starting with a defective, you have to think about the proportion of your testing. I'm not going to go into the math with it here. I'll be happy to take those questions offline or answer them after the presentation with you for those that are interested. But it's important to make sure that you keep your proportions or your sample augmented sample size roughly the same or multiples of your original sample size. That's a symmetry question that relates to the probabilities, okay? But it's important to do that because if you do, the fidelity of the results coming out to you are meaningful. If you don't, there's an entrenched error in there that you have to watch out for. So keep it straightforward. Just keep the same augmentation sample size or a multiple thereof, okay? That's going to be why it's important to know the cost of each additional specimen, right? Usually there'll be pressure to keep it low. Depending on where you are on the OC curve, that's going to make a big difference. So let's move forward and take a look at what that means. We're going to start first by looking at it from the increase of sample size. Here's 4 different curves that show an N increasing incrementally from 25 up to 50. And what you can see here is if I take bad quality maximum limit as 10%, right? That's the lower axis. You see the vertical bar there. And my probability of acceptance there of roughly 30%, fairly high. And if I increase that sample size, I get even higher along the lower axis. That's the key thing to remember is, you know, as my N, I go to the left on the lower axis. As you see that sample size moving up, right, you see the curves are being pushed to the left. That's key. And we're going to look more at that here in just a second. Okay. So the recommendation here is to set up your samples with contingency in mind. Start with the standard plan. That's what everybody likes to do, which is the C equals 0 plan, but plan for that failure. Be ready for it, right? Have a clear instruction set for yourself to know that if it crops up, I'm not scrambling around to know what I need to do. I already understand it. I understand I need to keep my proportion roughly the same as my original sample or a multiple thereof, and I'm going to go ahead and augment depending on what the economics of my expansion allow, okay? Key questions to always ask yourself as you start thinking through this contingency, right? Are my samples random and representative? We hear that a lot. Are my processes, are they an operator and assembler training? Are they substantially equivalent to my manufactured setup? Right? And is my supply chain stable? Why are these crucial? Because if they're not, what happens is your sample is less representative of truth and reality than you might want to accept. If you have any doubts about it, plan for what I showed down below. None of them are good, and that's why I encourage you to make sure all of these 3 bullet points up top are rock solid stable as you get into it. And here's why. let's look at what this sample actually means next, that we're originally gonna take and that we'll augment with. The sample is not representative of your complete universe. If it's a device that you've just started producing, well, if you're successful, and we all plan for that, it's gonna be around for decades, meaning that the universe of parts that'll get created out of it is open-ended. Therefore, the gaps around your sample, the frame of which you're taking to do these tests, is incomplete. That's okay, but you have to accept it and own it. That's why the stability of those processes, people, and parts is so absolutely crucial. Okay, let's keep going. How does it affect our confidence and our power, or our consumers' risk and our producers' risk? Here's where we're going to look at it in some detail, just to give you guys a flavor for it. Notice that what I've shown you here is the C values as you increase. Remember, we already had a failure, so we already got C equals 1. We're now looking at C equals 2. But as I increase them, right, the producer's risk is shown down in the lower corner, right, with the little red box. Okay, let's zoom in on that and see what happens. Go ahead and let's click in, and we'll see if we accept again a 10% LTPD, lot total percent defective, that's our patient risk. That ends up giving us a probability of about 12%. Okay, so this is for a sample size of a lot size of 500, sample size of 35, and we set that LTPD at about 10%. That may be high for some of you out there. You may say, "Oh, I would never do that for my patient risk," but it's just a starting point to give you an idea of how we can balance this. Now, let's say that we have to increase our sample size, as we've talked about. Keep going, and let's see what happens. Ooh, let's back it up just a little bit. I think we missed a click there. Okay, what you'll see, yeah, that's right. What you'll see is that if we increase that sample size and allow an additional failure, right? Our original curve is shown in the middle. Our increased sample size is the red curve showed on the left. If we get no additional failures, that's a lucky situation. We can't plan for it. If we allow for one additional failure above and beyond the one we started out with, we end up on the left, and that shows us that we have somewhere between, type's a little small here, I think it's about 17 and 18% lot total percent defective for the same probability of acceptance. That's the key bookends to think about your patient risk. It's going to go up, but you need to know by how much. Okay, and that's important because, let's move on to the next slide. Let's look at what happens now when we double the sample size. Okay, so we've doubled it. We're going to take a multiple of 2 over the original sample size. We'll keep this 5% lot total percent defective. That probably feels more comfortable to those of you in the device world. That gives us the same 12% of probability of acceptance. That's where our original curve is. It's in the middle. With one additional sample, we end up around 14%. Okay, the curve on the left, remember, is if we don't have a single additional failure in the augmented sample. Could happen, but we want to be prepared for if it doesn't work out that way favorably. What's the bookends of our risk? 5% to 14% bad quality in our outgoing product. Okay, that's the key. Understanding the bookends so that you can balance your risk with patient safety. Okay, let's go down. Let's keep on going here. The key takeaway, and it's a lot to cover in such a short presentation, is that your consumer's risk is your patient's risk, right? Augment your data set. If you're lucky enough not to have a second failure, you've actually got pretty reasonable product quality that you can balance that risk with. If you have to accept a second failure, at least you know how much additional patient risk you're taking on, okay? That's the key. And all of that's combined with your cost and time. Also equally important is that your sampling plans plan for more than just success. It's a pretty rare thing that industrial experimentation succeeds out the gate the first time. And that's why I encourage all of the folks that I work with to think about that potential failure and plan for it. It's very, very important. Okay, Thank you so much for listening.